And welcome back. Now we're at our third series of this STS series, 4-lecture series, where we talk about combinational logic. So far we've seen introduction to synchronous digital systems, state, registers, how those work, timing, that's a really important piece of it. Now we're kind of at the, don't worry about the analog element of it, let's just talk about the logic part of it. This is a little bit more fun, a little bit more digital, and thinking about the analog, the realities of the analog world are not as present here in the combinational logic world. So let's talk about combinational logic and jump on in. We start with truth tables, and maybe you've seen truth tables before, maybe you haven't. Turns out it's funny, I learned truth tables, how to do them, I think I was in 5th grade. We were doing basic truth tables. I think I saw them again in 8th and 9th grade. This is just me, I went to my school, different place across the world from here. But hopefully you've seen these before. If not, I'll try to go slowly with this. Here's a box. Truth tables are on combinational logic. If you remember from a lecture or two ago, combinational logic circuits are those that have no state and no memory. Some set of inputs, the output will always be the same. If I go back and put them back again, it'll still be the same. There's no memory to these things. This is just pure combinational logic, pure functions, if you will, in the 61A and CS10 sense. So this is a 4-input, 1-output box. I've got a Y here. On the right, you're going to see this is kind of how we typically draw this. And back in the days when you're doing truth tables, you might have drawn T and Fs. Stop doing that. You want to use 0s and 1s, and in fact, as you're counting them, you want to basically count up from like a nibble. Here's 4 bits, count them up, all 0s to all 1s. You don't want to put, like I've seen people draw these where they write T and Fs first, or T and Fs look too close together. And also they write all T's first. No, the first row should be all 0s, always, and the last row should be all 1s, however many bits you have, okay? So, this is a box. I could buy this box at Fry's Electronics, and this is whatever that box does for all 0s. What does that box do for all 0s and a 1? So what's actually interesting about this, I'm going to ask you a question. How many of these boxes does Fry's have to sell? That's a fun question. Think about how many different of these boxes they have to stock. I mean, if they had to have 1 each for all the different ones that have a different pattern here, I'll give you an example. The AND gate, which is true only when all of them are 1s, has a 1 down here, and a big old 0 for everybody else. That's one of the boxes they have to sell. They have an AND, okay? So how many other devices do they have to sell if they want to cover every single possible case? Think about it, and I'll give you an answer in a second. And welcome back. Here's how many. It's kind of cool. Turn your head sideways, so you're looking at this number with your left side here and your right side there. How many different bits do you have there? I count 16. 2 to the 4 is 16. Each possible bit pattern is a different box. How many different bits? We call that the signature of the box. How many bit patterns are there with 16 bits? 2 to the 16. That's 64,000. So you have to have 64 kibi. This means 64K, different F boxes if you're going to have this for everyone. If Fry's is going to stock every possible combination. Isn't that kind of cool? 64,000-ish. That's a lot, okay? So that's pretty cool, the way to think about that. Here's another truth table example. This is going to be 1 if one but not both of A and B are 1. By the way, I love this example. This example, if I said, Halloween is coming up, we're in the fall here, so Halloween's coming up. If a kid comes to your door and they say, trick or treat, they mean this table. This table is for trick or treat. This is a Halloween table. Why? It says trick or treat, but not both. Here's trick or treat, but not both, okay? So they mean it's a 1 if one or the other is true, but not both. What it means in Halloween, if you give the person a treat, you expect them not to toilet paper your house. The idea is a contract, right? If I give you the treat, you're not going to do a trick on me. So it means this table. This is the Halloween table. So remember, see this thing? Always remember this table as the Halloween table as an example of that. Pretty cool, right? By the way, I want to show you another way to think about this table. This is rarely taught. It's like pro tip. If you think about it, when A is 0, how does B relate to the output? It's exactly the same. When A is 1, how does B relate to the output? It flips it. it's like not B. So in fact, I can summarize this table by saying this is a two-row table. When A is 0, output is Y is just B. When output is 1, output of Y is not B. It's a kind of tighter way of thinking about the table. I want you to get used to that and comfortable with that. If I change this to any pattern of 4 things, by the way, how many I get to that. How many of these would fries have to have? For every one of those, I should be able to kind of reduce this into this kind of table. When A is 0, what is it? When A is 1, what is it? Okay? So that's kind of neat. By the way, if these were both 0, I would have written a 0 here. If these are both 1, I would have written a 1 here. If it's 0, 1, I write B here. If it's 1, 0, I write not B. So that's how you kind of compress this table to that way. Kind of neat, right? All right. Here's an example for the truth table of a 2-bit adder. Okay, we've seen this before. We used adders before in our last series of lectures. This again is a 2-bit adder, where the output now, I was saying before, well, there's a 2-bit adder without overflow, because sometimes you put some numbers in and it's bigger than that. So I had N and N and N output saying, well, somehow we don't worry about that at this early stage, whether it's overflow. But in fact, if I had a 2-bit adder, I mean, you can think about this. The biggest number of this guy can be 1, 1. That's 3. The biggest number of this guy can be is 1, 1. 3 plus 3 is 6. That's 1, 1, 0. I kind of knew that because I'm doubling this, and you double it, you just add a 0 there. So there's no way to think about binary numbers in that way. So I have to have 3 to be able to handle all the cases. C is really, here's the fun thing, C is really, should be 3 bits. And by the way, I haven't talked about this before, this slash tells you how many bits wide that line is. If you haven't talked about it before, that's the way to think about this. So this is a 2-bit adder. This is all the logic of a 2-bit adder. Again, I think of the grouping of A really being A1 and A0. Here's B really meaning B1 and B0. And here's C being C2 through C0. So let's ask a question. How many rows does this have? Well, just like before, the number of inputs is 4 bits of inputs. Therefore, that's a nibble input. Therefore, I have to handle all the cases of 16 different cases for that. Okay? Well, that's nice. I can do that. If you need me to build that, I could probably be able to build that. That's not a problem. Except that when I extend that to 32 bits, and now I've got 2 32-bit inputs, and this is an unsigned adder. We don't have to worry about anything other than unsigned values. And I've got this guy. Maybe this is 30. Maybe this is 32, and this 32 and 32, and this might be 33 again. What's the biggest output? The biggest output is there. This better be 33 bits because I've got all 1s with a 0 because I've doubled all 1s. All 1s is a 0. Okay, well, you might ask the question again, how many rows do I have? Anybody figure that out? Was that the right way to do this? Is the right way to build a 32-bit adder by looking at the truth table for it? I'm kind of trying to reveal that might not be the right way to do it. Well, how wide is this? That's an input 32 bits. That's input 32 bits. Well, before it was the total number of bits is my input. That's how many rows I have, 2 to that. I count 2 to the 64. That's a lot. That's 16 XB rows. Too many rows. Way too many rows. So this is not the way to do this. So let's actually take a step back. At some point, we'll talk about how to do that another way. I'm giving another example. Here is a 3-input majority circuit. I say majority, it's almost like 3 people are all deciding, should we go that way or that way? Let's all, 1, 2, 3, 1, 2, 3, shoot. And the majority wins. So for all zeros, let's do it. Let's see if this actually adheres to that. They're all zeros, majority wins, 0. If there's 2 zeros and a 1, 0 wins. Again, 2 zeros and a 1, 0 wins. 2 zeros and a 1, 0 wins. Every other case, there's more 1s than zeros. 2 1s, 2 1s, 2 1s, 3 1s, and then 1 wins, okay? We call this the majority circuit. That's kind of neat. This is like breaking a tie, breaking a tie for that. So that's kind of fun. So I gave you a couple of examples of truth table, and that's the basics of this. Sometimes we don't use the truth table to build circuits like for the adder. We might find a better way to do that. We'll actually talk about that later. But this is the way to think about this. You want to be writing zeros to 1s. You want to be counting from all zeros to all 1s in the way don't use T's and F's. And that's it. Thank you so much. We'll see you at the next lecture.